Hi guys, last video we saw how to convert a solid part into mid-surface. So in this video, I'm going to do the analysis on that particular plate which we made. So the dimensions of the plates are 500 mm cross 500 mm and it has a thickness of 2 mm. Material will be going to use steel itself, and the load we are applying is 1000 Newton at the right end, and the left end of the plate is fixed. So we'll be expecting somewhere around 1 megapascal stress in this plate. And there are basically three ways of modeling it. You can use a conventional shell or continuum shell or solid elements. So this video will be talking about how to do the same for conventional using conventional shell elements. So let's quickly go back to our model. So here we have made the part as a mid surface, although we had it in original form as a solid. All right, so part is there. Let's quickly define the property. So for property, we need to make a material first of all. I'll be making a macro or Python script in next video so that we don't have to do it again. Let's quickly define. One way to do is obviously you can copy your previous CAE file and then paste it and use it from wherever you want. For example, material will be already assigned and you need not to do it manually again and again. I'm just doing it for the reference or for sake of a video if someone starts it from the first time. Anyway, so how do we assign section? Before assigning, we have to make a section. Let's go create. So earlier videos we have seen if you are using beam or line elements, then you have to choose here accordingly what kind of section it is. And then we had done with the solids as well, homogeneous. But this video again, it's different from solid and the beam. Now we are using shell. So our section is homogeneous, right? It's homogeneous through the surface. So let's give homogeneous and make it plate, or let's keep material steel shell section. All right, so here are a couple of details it will ask. For example, shell thickness. How much is the shell thickness we want? Okay, as per our problem statement, we have it 2 mm, as we saw. 2 mm shell thickness we want, and material obviously steel we want to keep. So here are the number of integration point if you have done any course in Abaqus. So these are used for the calculations. And so basically what happens is when you have a local coordinate system and then you convert into node natural coordinate system, basically natural means -1 to 1, all the elements and their nodes are converted from -1 to 1, and at that time integration points are used for calculations. um, all right, we won't go into those details. Maybe I'll make another video on that, giving all the steps in the FEA. All right, so let's quickly assign this material. Great. I don't want to make any set. Choose the surface. Done. Steel section. Of course, shell offset, we want it to be middle surface. There are various ways you can define it, but in our case it is the middle surface of the 2 mm which we are talking about. If you have not defined the middle surface, then you probably accordingly you have to choose it. What it means is this particular surface is middle, and there is 1 mm above it, 1 mm below of it, because the shell thickness is 2 mm. All right, material is assigned and we have green colored beautiful plate over there. All right, so next thing is let's quickly do the meshing. Interestingly, in previous video I was talking if you have a different color what it means. Here it has something pinkish color, so does it mean it will give me structural meshing or not? Technically this part is very simplest part, and it gives you structured meshing. In other words, if it is not, what happens is I'll just show you guys. Assign mesh part, you go there, click here near to then this is what this means: free mesh, structure meshing, or sweep meshing. I will make another section on it. Let's quickly do a structure meshing would mean green color. All right, let's give 15. Okay, cool. Mm, let's mesh the part. We need to see what kind of elements we are using. So linear or quadratic, but what exactly is the type? Shell. So we're using shell type, right? So we don't see any more here the other types, for example, beam or those, because the model itself, the material assigned to it is based on the section we had decided. So that's why we don't see unnecessary elements over here. For example, solid and all those things, right? Cool. Let's quickly go and mesh is there. Assembly. We'll need to bring this part. Okay, we had already brought this part into assembly. What kind of analysis we want to do is to be defined under step. Let's do create general. All right, static, continue. We are not bothered about non-linearity right now. Dismiss. And all right, only thing pending is now how do we apply this load. So the load you can see is to be applied on the edge. It's a uniform load which is acting on the plate. So there are two ways we can do it. Either we can apply the load over a reference point the way we have done in the previous videos. If you haven't seen it, please go and check it. So basically there what you do is, I'll just give you the idea. You'll make a reference point where you want, for example in this case you want it to be on the right hand side. You'll make a reference point, and then using the coupling you'll be, for example I'm just choosing this particular, and then you'll choose node region for, all right, and you'll choose this edge and then do done. So that would make a coupling there. Of course the point I've chosen is on the left corner. You can make the point over center. Okay, that is one way. And then under your load module you can put a concentrated force on that particular point, but we are not going to apply it this way. What we are going to do is we'll be going to load and we'll apply a shell edge load. That's how we are going to do today. So we'll choose the edge of the shell where we want to apply the load. Now, very important thing is to understand what would be the units of this particular load. We know the length of this edge is 500 mm. Okay, so okay, one thing you guys can even before that I'll probably show you, we can even use this particular kernel command line interface for doing any calculations quickly. So we have a line load. When we say line load, it means force per unit length. So we are applying 1000 Newton per unit length, and the length of that particular line is 500 mm. So it comes out to be how much? 2. So 2 Newton per mm is the line load we are going to apply. Okay, that is how I bad boundary condition. I will apply shell edge load, continue. Okay, selected, done. So we are applying 2 Newton per mm. All right, we need to probably change the direction. We don't want it to in the compressive mode. So how do we change the direction? Very simple. We put minus over here and see. That's the magic. All right. So our load is applied. Let's provide the boundary condition. We'll keep symmetry encastered. I'm keeping encastered or else just to avoid any confusion. We'll choose the other end. We have chosen this end and do done. Okay, encastered, done, dismiss. All right, our model is set. Let's quickly run this job. We're running out of time already. Okay, plate shell. Okay, 80, just to avoid memory shortage. Submit. Alright, when you clicked here on the kernel command, it won't show you what is happening in your model right now. You have to come back and message area, click there. So our analysis is finished. Let's quickly check the results. What were we expecting? We were expecting somewhere around 1 megapascal, 1 megapascal, 1000 Newton or 1000 mm square. I hope we have obtained same. Okay, von Mises is showing somewhere around 1.3 megapascal. We are expecting 1 megapascal. Let's have a look at S11. Interestingly, we have 1.4 megapascal here. If you probably refine your mesh, you'll be able to get more accurate results. Well, even if you refine your mesh, you won't be able to get as close as to the theoretical value because we have given the boundary condition at the left end as fixed. So we are not allowing it to translate as well as rotate. In that case, we will probably need to provide better boundary conditions to capture the reality. I'll make another video of the same. Anyway, so this is how we do analysis for a plate sort of elements using conventional shell elements in Abaqus. Thank you.